All right, so once again, find the section in your notes competing for electrons. I'm going to show you a demonstration. I talked about it last time where I'm putting a piece of metal in different solutions and we're looking for which reactions occur. So let's go ahead and watch that.
So here's a demonstration. I have a solution of silver ion, silver nitrate. So far left, and we have copper 2, zinc, and then hydrochloric acid. And I have two metals, copper metal, which is the orangish looking metal, and then zinc, which is kind of grayish. So I'm going to put both metals in each of the solutions, and then we'll look for the noticeable difference. Two. I'll try to keep them separated from one another. We really don't need to put the copper metal in the copper solution. So we have those kind of blocked out there. So I'm not going to put the zinc in the zinc solution. And I will put both in the hydrochloric acid. And we'll do a little time lapse and see what happens. So again, here's what the zinc metal by itself looks like. And this is in the solution of silver. There's the copper at the top, there's the zinc. And then there's the zinc on the bottom. Does not look like this anymore. And then here's our copper metal in the solution of zinc ions. And here is our two metals in the hydrochloric acid. I don't know if you can tell, but if you look closely, there's some bubbles forming on the zinc, and it looks like nothing's happened with the copper. Definitely a change there. Definitely a change there to the zinc. Doesn't look like anything has happened to copper there, nor there, but the zinc has changed. So here's a demonstration. I have a solution of silver ion, silver nitrate. So far left, we have copper 2, zinc, and then hydrochloric acid. And that's
All right, so let's go ahead and fill in our table with the reactions that occurred. So when the zinc metal was placed in a solution containing silver ions, a reaction did occur. Likewise, when the copper metal was placed in the solution of silver ions, a reaction occurred. When the zinc metal was placed in a solution of copper 2, again, we saw a visible change in the zinc. It turned like black, telling us that a reaction occurred. Reaction between copper metal and zinc ions, no visible change was observed. So those substances did not react with one another. Kind of hard to see, but as I mentioned, when you place zinc metal in the solution of hydrochloric acid, there were some bubbles. Hard to see through the camera, but I definitely can see them. So a reaction does occur between zinc metal and H plus ions. There was no visible change that occurred when the copper metal was placed in a solution of hydrochloric acid. So what does this information tell us about the ions in solution and the metals? So something that should be kept in mind is that metals like to be oxidized. Metals like to lose electrons. Some metals like to lose electrons more than others. Likewise, cations, like these cations here, Ag plus, Cu plus 2, Zn plus 2, and H plus, they like to be reduced. And again, some want to be reduced more than others. So let's do this. Maybe in the margin or anywhere you have room next to letters B and C, I'm going to write the equations for any reactions or no reactions that occur. So let's go ahead and do that. And we'll start off with the first one here. So let's see, zinc metal plus silver nitrate. The nitrate ion is just a spectator ion, so I'm just going to write zinc plus Ag plus. And did a reaction occur? Yes, a reaction did occur. We don't really care about the products here. Of course, they would be zinc ions and silver metal, but all we're caring about here is if a reaction occurred or not. All right, let's take a look at this one. So the copper metal with the silver ions, those also reacted. Zinc and copper 2, a reaction occurred. Zinc and H plus ions, a reaction occurred. Copper metal and hydrogen ions, no reaction occurred. A little out of order here. So copper metal and zinc ions, I think that was another one we did. No reaction occurred. So what we want to do is we're going to set up a table showing the tendency to gain electrons. And so I'm going to set this up. Actually, I'm going to make two lists. One that shows increasing ability to be reduced, and the other decreasing ability to be oxidized, or maybe we'll do increasing ability to be oxidized. So I'll set it up a couple different ways. So we'll start off with the ions. And so what we want to look at is we're going to compare the ions. Zinc plus 2, copper 2, silver, and H plus. And what I want you to do is think about which ion wants to be reduced the most. So again, the ion that wants to be reduced the most is going to undergo any reaction in order to produce the reduced form of that substance. So the reduced form of Zn plus 2 is just Zn. Cu plus 2 would just be Cu. Ag plus would be Ag, and H plus would actually be H2, hydrogen gas. That's why we saw the bubbles. So go ahead and do this. Pause the video and put these cations in order of increasing ability to be reduced. Increasing ability to gain electrons. So start off with the substance that wants to gain electrons the least, all the way up to the substance that wants to gain electrons the most. Go ahead and pause and do that now, please. All right, so here's what we get. Zn plus 2 wants to be reduced the least. H plus wants to be reduced more than Zn plus 2. Cu plus 2 wants to be reduced more than H plus, and Ag plus wants to be reduced more than any of these substances. So hopefully you got to that order. Now here's something else we can take a look at. Look at these two equations here. So I just took this first equation and I wrote it out, and then I wrote it in reverse as well. And so here's what we're looking at. We're looking at a comparison of Ag plus to Zn plus 2, even in this equation. So the question is, what wants to be reduced more, Ag plus or Zn plus 2? Well, we saw that when we mix zinc metal with Ag plus, a reaction did occur, and you do make those products. If we were to do it the other way around, so if this reaction here, we'll call that reaction 1, if reaction 1 is spontaneous, then what can we assume about reaction 2, the opposite of reaction 1? Well, if reaction 1 is spontaneous, then reaction 2 is non-spontaneous. This reaction does not occur, so that tells us that Ag plus wants to be reduced more than Zn plus 2. And we can do similar comparisons with any of the other substances, and that's how I got that list. So Zn plus 2 does not want to be reduced. Zinc prefers to be Zn plus 2 and not zinc metal. Conversely, Ag plus really wants to be reduced. Silver does not want to be Ag plus, it wants to be Ag. Now, we can do this as well. So this is a list of ability to be reduced. So these are reductions. What about oxidation? A list of the substances that want to be oxidized. How about that? Why don't you pause the video and come up with a list of increasing ability to be oxidized. Substance that wants to be oxidized the least, all the way up to substance that wants to be oxidized the most. Go ahead and pause and do that now, please. So I mentioned before that silver does not want to be Ag plus, but rather wants to be Ag. So it wants to be oxidized the least. all the way at the end there, zinc does not want to be Zn, it wants to be Zn plus 2. So zinc metal wants to be oxidized. Whoops, I said that the other way around. Zinc does not want to be zinc metal and wants to be zinc ions. I wasn't listening to what I was saying there. So Zn really wants to be oxidized. It does not want to be as Zn metal. All right, let's add something here. If a piece of nickel metal is placed in separate beakers containing Ag plus, Cu plus 2, H plus, and Zn plus 2 ions, a reaction would occur in all but the Zn plus 2 solution. Where would nickel belong in the table you made in C? Let's do the table, this same table here, the table of reductions. Go ahead and pause and add to that list, please. All right, so given that the nickel metal would react with everything except for the solution of zinc ions, what that means is that nickel plus 2 wants to be reduced less than everything except Zn plus 2. So the only substance that wants to be reduced less is Zn plus 2. And again, if we were to add it to this list here in terms of the ability to be oxidized, the nickel would go right here between the zinc and the hydrogen. So nickel wants to be oxidized more than hydrogen, but not as much as zinc. All right, so what does all of this have to do with our galvanic cell example that we talked about before? So there's a relationship between voltage and the tendency to gain electrons, as we'll see in a second. Let's start with this though. Equilibrium and redox. A battery has reached equilibrium. So the reaction inside a battery has reached equilibrium when the potential is called the voltage produced by the reaction is 0.00 volts. Well, let's take a look at the relationship between the tendency to gain electrons and voltage. All right, what I'm going to show you in just a second are known as a table of reduction potentials. And so what this table shows, here I'll show you now. All right, what this table shows is the ability of something to be reduced as compared to hydrogen. So notice that hydrogen way down here, so whoops, see if I can write on this. Reduction of hydrogen, I know it's kind of hard to see, but you have the same or very similar table in your book on page 667. The reduction of H plus to H2 has a voltage of 0.000 volts. So everything, all the other values on here are in comparison to hydrogen. So here's how it works. Actually, no, we'll get to that next. These values, these numbers here, the symbol that we use for reduction potential is E naught. So that naught means something, same as before. So these values are dependent on temperature. So that being solutions that have a temperature of 25 degrees Celsius. Concentration, and that being solutions have concentrations of 1 molar. And then if there's any gases present, the pressure of the gases being 1.00 atmospheres. So we won't look at any other situation where concentration is not 1 molar, temperature is not 25 degrees Celsius, pressure is not 1 atmosphere. So if it doesn't say so, we'll assume these standard conditions. So notice at the top it says table of standard reduction potentials. These are reduction potentials at standard conditions. All right, so here's how it works. If the sign of the voltage is positive, we're talking about on this table here. So that's basically anything on the right side. Now keep in mind that this right side is a continuation of the left side. So these are not two separate tables. So anything, I'm going to say it this way, anything below hydrogen, what that means is the oxidized species. By oxidized species, I mean whatever's written to the left here. So Sn plus 2 and Cu plus and Br2. Those are the oxidized species, whatever's on the left side of the half reaction. The oxidized species has a greater tendency to gain electrons than do H plus ions. So everything below hydrogen wants to be reduced more than hydrogen does. The opposite is also true. If the sign of the voltage or reduction potential is negative, then the oxidized species, so Li plus, K plus, Al plus 3, wants to be reduced less than H plus does. So anything above hydrogen wants to be reduced less than hydrogen does. Now, we don't have to always compare to hydrogen. In fact, we're usually not comparing to hydrogen. We're comparing two different substances to each other on this table. Here's how it works. The substance with the higher reduction potential wants to be reduced more. And so this will be especially important when we're looking at galvanic cells and looking at spontaneous reactions to see which substance actually is reduced during that reaction. So let me go ahead and flip to here. So we have those values. Should have filled this in already. All right, so let's do this. Let's learn how to calculate the voltage associated with a redox reaction. On second thoughts, I will stop the video here for now, and then part 2 of the video, I'll show you how to calculate the potential difference or the voltage for a redox reaction. Thanks for watching. Stay tuned for the next video.